Hello folks, today I'm tackling a problem on HackerRank called Lisa's Workbook. This is an easy difficulty problem, but when I saw it, I thought it was pretty interesting, so I thought I'd just check it out with y'all. As usual, I'll go over the problem, give you some time to do it on your own, and then go over my solution. So let's check it out. Lisa just got a new math workbook. A workbook contains exercise problems grouped into chapters. Lisa believes a problem to be special if its index within a chapter is the same as the page number where it's located. The format of the book is as follows. There are n chapters numbered 1 to n, so we're indexing from 1. The ith chapter has a certain number of problems numbered from 1 up to whatever that number is, and each page can hold up to k problems, and only the chapter's last page can have fewer than k. Essentially, this is like the remainder of the problems. So here's my representation here. You're going to be given a list, which is essentially like the workbook. The workbook, by the way, is like an outline for the book, which is like a weird way of thinking, but essentially each value is representing each chapter. So the first chapter has a certain number of questions, in this case 4. But if you have k of 3, meaning that there are only 3 questions per page, then chapter 1 has to take up 1 page of 3 questions, and then another page of 1 question, essentially the remainder. And that's what I have here. So here I've kind of re-represented the workbook and like re-represented that as the book with its pages. Question 1 is special, according to Lisa, because its question number, again within the chapter, is the same as the page is on. So that question 1 is a special question. Therefore, there's so far 1 special question. Chapter 2 has 2 questions. So notice something, we're now on page 3, and we reset the count, right? The question is per chapter. So this is question 1 and question 2 for chapter 2. There are no special questions here because there is no question 3. So there's nothing special here. Chapter 3 has 6 questions, and so that basically is 2 full pages of questions numbered 1, 2, 3 for page 4 and 4, 5, 6 for page 5. And sure enough, there's a question 5. So there's a special question on that page. And the same thing goes true with chapter 4 and chapter 5, and you can probably tease that out yourself. But effectively, we have in total 4 special questions. I'll give you some time to do this on your own before I go over my solution. Good luck. Okay, so I think my algorithm is going to be something as follows. I'm going to keep track of the number of special questions as a running count, as well as the current page we are considering. So each page, because we have to like iterate through one, I need to keep track of that as well separately. And then I'm just going to go through our list. So for each chapter in that given workbook array, we can divide the chapter by k, but you have to keep in mind, if you divide by k, you get like the number of like full pages as well as like a remainder. So I need to do this like modulus operation of like getting how many remainder, because that needs to be put on its own page and be considered separately. And so let's say we get a count of full pages, like let's say it's 3, then I'm going to iterate through each of those 3 pages. I'm going to check to see if the current page being considered is within the range of the questions for that page. And if it is, then I'm just going to add 1 to the count. And if not, then nothing happens. And then we just like increment to the next page. And then we'll go through each of those like full pages. And then once we're done with that, we need to consider any remainder questions, because that needs to be handled a little bit separately. So let's look at the solution in code. This is Python, but I hopefully explained it enough that you can use it for other languages. All right, here's our function, our workbook function. We have a running count, which is the answer that we're going to be returning essentially, as well as the current page that we're on. Then I'm going to go through our given array. This is like the workbook array, which has a question count. So I'm going through each chapter essentially. So the question count is like for that next chapter. And here I have this function called divMod, which is a function in Python. It works like this. You give it 2 numbers. It will divide those 2 numbers together and give you the whole number of divisions, and then as well as any remainder. So I'm basically teasing that out here. Here I have the number of pages added, full pages I should say, and these are the remaining number of questions for that. So I'm going to consider them separately down here. So here I'm going to go with a range. I'm going to go from 1 up to the number of pages added. Range is exclusive, so I have to add literally 1 just to keep the actual number of pages added as in the page number. And here I will get the new chapter page from that. So each time I go through this loop, it'll be like the new page for that chapter though. So for example, if I go back here for chapter 3, for example, this is page 1 for chapter 3, and this would be page 2 for chapter 3. That's what I mean by that. So the next thing I want to do is consider what questions there are. What is the question number, I should say. For the first question on that page, you need to kind of figure that out. There's a little funky math here. I know it looks a little complicated. Here's how this works. I'm going to consider the new chapter page -1 times k plus 1. How does that make sense? For chapter 3, for example, this will be page 1 of chapter 3. I want to basically figure out question 1 is the first question on that page. For chapter 3, page 2, that would be 4. So how would I do that? I would take the previous page number, again, within the chapter. So this is page 1 for chapter 3. I'm going to say page 1 times k, or 3 in this case. That will give you 1 times 3. That gives you question number 3. And then just like add 1 on top of that. That's how I got to 4. That's literally it. I'm taking the current chapter -1, so I'm getting like the previous page within the chapter, times k, which gives you like the last question on that page, and then you just add 1 on top of that to get the next question, which will be the first question on that current page. And then the last question on the page is just the first question plus k, but because of how math works, you do -1, right? Honestly, folks, math is just not, me and math just don't get along. If you find a better, more efficient way, please let me know, because I think that this could probably be cleaned up a little bit. I have my first question on the page. I have my last question on the page. Basically, we're checking to see if the current page number, which again, we're keeping track outside of the loop, if that is within that range, since it can only be, there's only one possibility for per page. I don't need to like do any more complex stuff to consider. This will give me a Boolean, true or false, if the current page is within that range. Notice this is inclusive. I'm doing less than or equal to here. If this value is true, then I'm going to add 1 to the count. That's what this means. The computer considers true to be 1 and 0 to be false, so that's why I can like do math with Booleans. It's kind of weird. And then I'll just increment my page count by 1 because we're going through whole pages here for this. Once you're done with this for loop, then you just need to consider any remainder questions. You kind of have a similar math to before. I just need to keep things a little bit different. I'm taking my last full page times k plus 1. So it's similar to what we had here. And then instead of adding k, I just add the remainder questions to get my last question on the page. Same logic as before here. And you increment your pages as well, because you have separate pages when you have the remainder. It's just its own page essentially. And then we return the count, and that should work. So let's run some code. That looks like it's good. Let's submit some code. Oh yeah, so good. All right, so let's consider some time complexity. This is constant time, just making some variables. This is big O of n. You're going through the list one time. This is math. That's nothing. This is a for loop. This is interesting because we have like some modulus operation going on here. So this is like big O of something. This question count, that has nothing to do with n actually. So this is a different variable. So in the problem, we're told all these things are between 1 and 100, right? So at worst, we're talking about the worst case scenario. This is p mod k, right? K is between 1 and 100, and p is the value within this list, this question count, right? So at worst, this is like the worst case scenario, which is what we consider for big O notation. That's at most 100 mod 1, which will yield 100, which is, I mean, that's just constant time, right? So that's, I don't know if that's even worth considering, to be honest. So I would say that this for loop, even though it is a for loop, is like insignificant, relatively speaking. All this stuff is math, so it's nothing. That's all constant time. This is constant time stuff. So everything here is, I think, constant time. So I think at most this is big O of n, I believe. So let me say total. I'm going to say your big O of n. At worst, your big O of n times big O of p mod k. But I'm going to say, that's just big O of n, because I don't think I'm going to consider, this doesn't, I don't think that's like worth talking about, to be honest. Hope that helps. Folks, if this is the kind of content you enjoy, please make sure to like, subscribe, do all the good things, and I will see you next time.